Okay, yeah. So we are having, let us define the vector field A to be psi and the phi. These two are the arbitrary scalar fields. So we are having now the divergence would be phi. This would be what? Phi or phi, whatever, and xi. Okay, and this is going to be equal to nebula square. This would be phi here, xi here, plus the divergence of these two fields. Okay, and the phi nebula or the del operator xi dot n outward, because we can put a value here also. Now we will put. So this is what I have done it here. This is basically a scalar field dot n dA. Okay, so not integrating it, so let's take only this integrand inside. So it is equal to phi partial of the xi. Okay, this is basically the normal derivative of the surface S, and it's directed outward from inside the volume V. Okay, so now let's substitute into the divergence theorem, and we will obtain, or we get, Green's first identity. So the Green's first identity is this integral V phi scalar field nebula square del operator another scalar field plus dqx equal to integral of closed integral over surface phi, the normal derivative at s of the phi xi into dA. So we can write the same equation interchanging, instead of phi here I can interchange it with xi. Okay, and we can then subtract it. We can interchange these two and then we can subtract it. So what we will, if we do this thing, we are going to get Green's second identity or the Green's theorem. That's basically phi nebula square xi minus phi nebula square phi dqx. Okay, we just interchange it, and if we are going to interchange and subtract it, this will turn what? This minus would be what? Minus only to that, so this will be 0, and this would be equal to integral over the surface phi d phi by this will be partial dA. That's right, dA here. So by interchanging and subtracting it, we have obtained a Green's second identity, which is called the Green's theorem. So the Poisson's equation, the Poisson differential equation for the potential, we can convert it into the integral equation if we are going to choose the particular phi. Let's say we are choosing a particular phi as 1 by r equal to 1 by absolute value of x minus x prime. This would be we are choosing a particular phi as 1 by r x. Okay, this we have chosen. So what is basically x here? X is the observation point, and x dash is what? X dash is the integrable, or sorry, integration variable. Okay. Now, if suppose I am going to put, now I have taken now capital phi and the capital phi. If I am going to equate these two also, going to put it equal to the scalar potential, and if you are going to make use of the nabla square international, the scalar potential equal to minus rho upon epsilon naught. Okay, and we can say the nabla square upon 1 by r is going to equal to minus 4 pi delta direct function. Terms of direct delta function was what? X minus x prime. So we can very easily write the Green's second identity or the Green's theorem using this. Putting this into that, we get integral of the v minus 4 pi phi x prime delta x minus x dash plus 1 by epsilon naught r rho of an x prime d cube x, and this is going to equal to the integral closed surface. We are taking this phi partial of this dash 1 by r minus 1 by r dA prime. Okay, so now if suppose I have said that what is basically x, it is the observation point. So if the point x lies within the volume V, we can get the scalar potential as what? We can get phi of an x equal to 1 by 4 pi epsilon naught integral v rho x cube x prime by r d cube x plus 1 by 4 pi closed surface over surface S 1 by r by n prime minus phi the partial of this n prime one by r dA prime. Okay, so if x lies outside the surface, then the left hand side would become equal to 0. Okay, and it is said that it is consistent with the interpretation of the surface integral as being the potential due to a surface charge density sigma is equal to epsilon naught partial of this d phi by this thing. Okay, and a dipole layer minus epsilon into phi, epsilon naught, so phi. So, and if we have if as there would be discontinuities in the electric field and the potential, so it will then lead to zero field and the zero potential outside the volume V. Okay, so the observations or basically the two remarks that are also given the two remarks that are given here are that we have just derived. The two remarks are basically mentioned that if the surface S goes to infinity and the electric field on the S falls faster than 1 by R, then the surface integral vanishes. Okay, and this will result with the scalar potential that we have done without boundaries. It will reduce to that the scalar potential without the boundaries, because here we have calculated taken the boundaries here. So for the second remark that is given is that for a charge free volume, the potential anywhere inside the volume, that would be what, the solution of the Laplace equation in terms of the potential and its normal derivative only on the surface of the volume. Okay, that means the potential anywhere inside the volume, which is basically the solution of the Laplace equation, it is expressed in the last equation or the expression, okay, in terms of the potential and its normal derivative only on the surface of the volume. Okay, and let's now move to the boundary conditions. So let's say if we are having an arbitrary specification here phi, or if I take a Cauchy boundary equation of a partial of the partial of the phi by the partial. Okay, let's take on the uniqueness of the solution with the Dirichlet or the Dirichlet or the Newman boundary conditions. So what boundary conditions are going to be appropriate for the Poisson or the Laplace equation to ensure that a unique and a well-behaved solution will exist inside the bounded region? So we are going to take first the Dirichlet boundary conditions or the Dirichlet problem. I'm sorry if I'm pronouncing this as wrong. Okay, so we know that if we are going to take a normal derivative, it is going to become a Newman boundary conditions. Okay. Now what we basically want to show now, that we have a Poisson equations. We have a Poisson equation that is equal to minus rho by epsilon naught, and this has the uniqueness of the solution we are going to say inside the volume V. Either we are going to subject it to the Dirichlet or we are going to subject it to the Newman boundary conditions on the closed boundary surface S. Okay. So now we suppose that let's suppose there are two solutions for phi 1, phi 1 and the phi 1 2. It's satisfying the same boundary conditions, and the difference would be equal to u phi 1 minus phi 2 minus phi 1 would be equal to u, and so this Nebula square or the Laplacian of the u is going to be u0 inside V, and u is equal to 0, or the partial equation, the partial derivative that we have defined u with respect to n. Okay, this would be equal to 0 for Dirichlet and the Newman boundary conditions. So from the Green's identity, first identity, from the Green's first identity, let me again write what was basically the Green's first identity. The Green's first identity was this V into dA. So from this first identity, if I am going to make this arbitrary scalar field phi is equal to psi, okay, and equal to u, we can say this would be what? If we are going to write u everywhere here, u nebula square u plus dot u dqx equal to s u n dA. So with this specified property of u, this is going to reduce to the v absolute value of the u square dqx. Now whether we take a Dirichlet or a Newman, it is going to reduce to this, because, and this means basically what? The gradient is equal to 0. Consequently, inside V, u is constant. So for the Dirichlet boundary condition, u is equal to 0 on S. That's so that inside V, this phi 1 is equal to phi 2, and the solution is unique. Similarly, we can say for the Newman boundary condition, the solution is unique. So for this we are going to even have a unique solution for a mixed boundary solution. That means the mixed boundary condition would be the Dirichlet. For one part we have the Dirichlet and the other part we have the Newman. Okay. So the other thing that should be clear, that the solution to the Poisson equation with both phi and this partial of the phi with respect to n, it is specified arbitrary on the closed surface. There is a Cauchy boundary condition that does not exist, because since there are unique solutions for Dirichlet and Newman conditions separately, and this will in general not be consistent. Okay, so now let us take the solution of the electrostatic boundary value problem with the green function. That means we are now want to obtain the solution of the Poisson or the Laplace equation in a finite volume V with either the Dirichlet or the Newman boundary condition on the bonding surface S. Okay, so we know that earlier we have taken this psi equal to 1 by absolute value of x minus x dash. This we have taken, it being the potential of a unit point source. So I am going to put the nebula or the Laplacian phi here, phi equal in terms of direct delta minus 4 pi delta x minus x bar. So this function is only one class of function depending upon the variables x and x prime, and they are called as green functions. Okay, so that are going to satisfy this equation only, and in general we are going to have the Laplacian square prime g x comma x prime equal to minus 4 pi delta x minus x prime, where we know that this g is going to be equal to 1 by x minus x prime, the absolute value, plus f of n x comma x prime, and with the function f is satisfying the Laplace equation inside the volume V, and it would be a nebula square f x comma x prime equal to 0. So in facing the problem of satisfying the prescribed boundary equation on phi or the normal derivative of phi Okay, let's obtain using the Green's theorem the generalization of the let's take this thing. Okay, let me again write the equation. We know that we have obtained the Green's theorem by interchanging the arbitrary scalar fields, and then what we have done, that the Poisson equation for the potential we have converted into the differential equation into an integral equation. And how we converted the differential equation into an integral equation? We have just put xi equal to 1 by r, and that we have basically said it is equal to 1 by x minus x prime, one by x minus x prime, and where we have said the x is the observation point and the x prime is basically the integration variable. Then later on what we have done, we have put the small phi by a capital phi scalar potential, and we have obtained the equation or expression for a point which is lying x within the volume V. That means what we have got, this phi of an x equal to 1 by 4 pi epsilon naught over the volume V, rho of an x prime by r d cube x prime plus 1 by 4 pi over the closed 1 by r normal derivative of this phi minus phi normal derivative of 1 by r dA. So dA prime. So let us take the generalization of this equation. Okay. So the generalization of this equation, it will be equal to simply 1 by 4 pi epsilon naught over the volume rho of an x prime g of an x comma x prime d cube x prime plus 1 by 4 pi closed surface s g of an x comma x prime partial of an phi minus the prime scalar potential of this at x prime arbitrary, this would be the normal derivative of the gx comma x prime. Okay. So for the Dirichlet boundary condition, we say that the g x comma x dash equal to 0 for x prime on s. Then the first integral that we have mentioned in the previous equation is going to vanish it. Okay. And we are going to get some expression with that. Similarly, we can use a Newman boundary condition. So the first choice we can very simply take for the Newman boundary condition partial. We are going to put a n derivative. I am putting g to denote Newman gn x comma prime equal to 0 again for x prime on s, and we will make the second integral vanish, and when we are going to apply a Newman boundary condition, we are going to see that it's the second equation comes to very simple. So this closed surface that I was mentioning, writing a long expressions, it just becomes equal to minus 4 pi. Okay. Now if I am going to use on S, it would be minus 4 pi by S. S is basically what? The total area of the boundary surface. So we can simply add and we can simply write the solution including these equations. We have to only include the average potential of the average value of the potential over the whole surface, this thing. Now we know that the product of the scalar potential and the charge of a point object, we can interpret it as a potential energy. So if a point charge q I is brought from infinity to the point x, okay, so we are bringing this point charge from infinity to the point x in a localized electric field, and that described by the scalar potential phi, and this scalar potential vanishes at infinity. So we know the work done on the charge, and hence the work done on the charge defined by the potential energy, it would be equal to the W is equal to Qi and Wi phi xi. The potential phi, it can be viewed as produced by an array of n minus 1 charges, where n minus 1 charges Qi we are taking from j is equal to now here 1 to n minus 1. Okay, then the potential would be phi of an xi equal to 1 by, this is an x, 1 by 4 pi epsilon naught summation of the n minus 1 by from j equal to 1 to n minus 1 that we have taken it, qi upon x minus or xi minus xj. ठीक है. So we are basically getting we can very easily calculate the what is the potential energy. We can say the potential energy of the charge qi. It would be definitely, we have to just put it here qi, and this expression would be respected because this is the value of this thing. So the total potential of all the charges due to the force acting between them would be what? It would be equal to W is equal to 1 by 4 pi epsilon naught sigma I is equal to 1 to n. Another summation sign would be for the j less than I, j is less than I, qi qj by xi minus xj. Okay. And if we are going to get, we want to obtain a more symmetric form, we can simply divide it by 2 and we were going to, it would make 1 by 8 pi. Okay. And if we want to here understand I is equal to j like an infinite self energy terms, then this double sum will get omitted. Okay, so this not a double sum will get omitted, but these two terms, because we are taking now I and j as both equal. Here the j is less than I. Okay, so if we are having a continuous star distribution, the potential energy will then become 1 by 8 pi epsilon naught double integral. Instead of summation, for a continuous, definitely it's going to become the double integral rho of an x and the rho of an x prime by x minus x prime d cube x and the d cube x prime. Okay, so we can note that one of the integrals in this is basically, we have taken two integrals. So the one integral is basically the scalar potential, and therefore is going to become 1 by half of the rho x phi x d cube x. Okay, so you can see I have derived so many equations here in sum of integral, summation, 4 pi epsilon naught. Earlier it was 4 pi epsilon naught, then I took an 8 pi epsilon naught because we wanted to get a symmetric form. So all these are expressing our electrostatic potential energy in terms of the position of the charges and the interaction between them, which is happening due to Coulomb force. So we have also an alternative approach to emphasize the electric field and to interpret the energy as being stored in the electric field surrounding the charges. For that we make basically a Poisson's equation to eliminate the charge density from it, and once we remove the charge density we get W is equal to minus epsilon naught upon 2 integral of phi the Laplacian of an xi and dqx. Okay, so we can integrate it by part. And we will going to get is going to equal to the, this is minus, is going to equal to the minus, is going to be equal to positive epsilon by 2 integral of absolute value of the nebula xi square d cube x, and this is going to be equal to epsilon by 2 e square d cube x. So where the integration is all over the space, and in this equation all the explicit reference to charges, you can see that we have not mentioned any explicit use of any charges here, and so they have also gone, and the energy is basically expressed as an integral of the square of the electric field, you can square of the electric field all over the space, and this leads to integrand as a energy density vector. This was capital W. Now we are getting an energy density small w equal to epsilon naught upon 2. This is very simple. We have just d cube x I have just removed because it's very even obvious, okay, because we have just removed the d cube x and integral, and we have got a energy density W. So okay, let me do complete only. Okay, so this energy density W, it's positive definite, and consequently its volume integral is going to be non-negative, and this is going to be contract our own the previous impression from the potential, that the potential energy of the two charges of opposite sign is negative. Okay, and this is due to that this equation contains the self energy contribution of the to the energy density. Okay, whereas the double sum that I have used, the double sum, double integral, or the double sum, that do not contain the self energy contribution to the energy density, and because of this contradiction, one is having a positive sign and the other is having a negative sign. So let's take suppose we have two charges Q1 and Q2. Let's say we have two charges Q1 and Q2. We know that the electric field at the point E with the coordinate x is basically E is equal to 1 by 4 pi epsilon naught Q1 x minus x1 upon x minus x1 the whole cube plus 1 by 4. Similarly for the other Q2 we can say by putting a this was, let me write it here. Okay, x2 upon 1 by x minus x1 the whole cube. Okay, so we can say that the energy vector, it would be what, 32 pi square epsilon naught W, it would be equal to Q1 square x minus x1 is power 4. Similarly for a Q2 square x1 minus x2 is to power 4 plus twice of the Q1 Q2, I am writing it here, twice of the Q1 Q2 x minus x1 into x minus x2 by x minus x1 the whole cube and x minus x2 the whole cube. Okay, so these, if we are going to see these first two, we can very easily see that these first two are basically the self energy contributions. Okay, and the third term is going to give the proper result for the interaction potential energy. If you want to show that this third term is basically giving the proper result for the interaction potential energy, we are going to integrate it over all space, and we are going to get W is equal to Q1 Q2 by 16 pi square epsilon naught into this integral, okay, consisting of both x1 and x2. So if we are going to use the change of variable by psi, okay, now we are coming to an interesting capacitance equations shortly. So what we basically got, this the equal to Q1 Q2 upon 16 pi epsilon naught square integral of the x minus x1 and then x minus x2 by x minus x1 the whole cube and x minus x2 the whole cube dqx. So this would be equal to, we are now taking a change of variable, that this is equal to basically equal to the rho x minus x1, not this one rho, but x minus x1 upon x minus x2 is equal to rho is this thing. Then we basically, this becomes basically what? This becomes basically 1 by 4 pi epsilon naught Q1 Q2 upon x1 minus x2 plus, into 1 by 4 pi rho again by plus n rho plus n upon rho cube absolute of the rho plus n cube d cube rho. So n is a unit vector in the direction x minus x1 minus x2. So we can rho 1 plus n that I have mentioned there, rho plus n the whole cube. This is basically equal to what? Negative of the negative gradient about this 1 upon rho plus n, and this would be an absolute value. So the forces between the charged bodies can be obtained by calculating the change in the total electrostatic energy of the system under small virtual displacements. Okay. Now, if in the immediate neighborhood of the surface the energy density is what? W is equal to epsilon naught upon 2 the square of the electric field, and this is equal to upon twice epsilon naught. So now if we imagine a small outwardly displacement delta x of an element, delta A of the conducting surface, the electrostatic energy decreases by an amount that is the product of the energy density W and the excluded volume delta x delta A. That means what I am saying, that the delta W, not I am saying, it's basically mentioned, I am saying that only, minus sigma square delta A delta x upon 2i epsilon naught. Okay. So this means that there is an outward force per unit area that's equal to sigma square by 2i epsilon naught, and it's equal to W. We have taken to mention W is only at the surface of the conductor. and this result is normally derived by taking the this result is basically normally derived by taking the product of the surface charge density and the electric field with the taken with the with care taken to eliminate the electric field due to the element of the surface charge density itself. So now suppose if we are going to come to the capacitor soon, just in 1 minute. We are not taking a system of n conductors, and each of the n conductors has the potential V. So the total charge would be what? Qi. Okay, and we are taking it this I is here 1 to n. So the electrostatic potential energy can be expressed in terms of the potential alone, and the certain geometries that are basically called the coefficients of the capacity. For a given configuration of the conductor, the linear functional dependence of the potential on the charge density implies that the potential of the ith conductor would be Vi summation of the to the n. J is equal to 1 Ij Q of an I or Q of the J. Okay, so this depends upon this row Ij and this is a Qj. This depends upon the geometry of the conductors. So these are the equations we are going to we can invert to yield the charge on the ith in conductor. This was the potential of the ith conductor. Now if we wants to take the charge of the ith conductor in terms of the potential, we know Q is equal to, from J is equal to 1 and the Qi is equal to Cij Vi. Okay, so this C, you have seen this C here. So these coefficients are called the capacitances or the capacitances, while Cij I is not equal to J, they are called the coefficients of inductions. Okay, if we have a Cii, it means the capacitance. Okay, or the capacities. If we say I is not equal to J, we say these are the coefficient of the induction. The capacitance of the conductor is therefore the total charge on the conductor when it is maintained at a unit potential, and all other conductors being held at zero potential. Similarly, the capacitance of the system of the conductors is also defined. Now suppose we have two conductors that are carrying equal and opposite charges in the presence of other grounded conductors. So we can define it in terms of the ratio of the charge on one conductor to the potential difference between them. Okay, so this equation that I have just mentioned here, we can use to express this. We can use to express this capacity, and we can say that for system of conductors, W is equal to half sigma I is equal to 1 Q B. Okay, and this is equal to half and I equal to 1, J is equal to 1. Both are the double sum we are having, Cij Vi Vj. So this we have derived here. So now let's take a variation approach to the solution of the Laplace and the Poisson equation. So the variational methods I am going to use now. These are also being used. So let's say that if that the physical systems in equilibrium, they have minimal energy content and generalized to the consideration of energy like functionals. So let us now take a suppose a functional I of the absolute of this phi, not absolute but I am taking a functional here. So let's draw bracket here, equal to half integral of v phi, again we have a phi, and would be d cube x minus v g phi d cube x. So this function phi x is a well behaved inside the volume and on its surface, and this gx is a specified source function without singularities within the V. So we can examine the first order change in the functional when we are going to change the phi to the phi plus delta phi. Here the delta phi is not a direct delta function, so we are doing the modification here, delta phi of delta phi, and if we do the modification of the delta phi of this x, it's an infinitesimal within the V. So the difference would be what? Difference would be delta I equal to I phi plus